Good evening, everyone. Welcome to the Problem Solving and Doubt Clarification course for the NPTEL course on water and wastewater treatment. We are in week 7 now, and as you all know, the course instructor is Dr. Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistants. My name is Akash Saha, and I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. So we will quickly go through the contents of week 7. So in week 7, we started with the water treatment, where we first saw about the water demand and what are the various demand periods of various water and wastewater structures, the population forecasting, the per capita water demand, and the variability in the water demand. And then we moved on to the water quality parameters, where we discussed about the BIS 10500, which is the standard code, and many surface quality water quality parameters like the turbidity, pathogens, disinfection byproducts, lead, copper, etc. And we also saw the case studies of Joshimath and Ganges at prestigious place. And then we moved towards the overview of the water treatment, where we saw the layout of the water treatment plant, the various unit operations for the surface water treatment, the characteristics of the particles that has to be removed, their electric charge, the concept of electrical double layer, and the particle stability. And moving on to the physical-chemical treatment, we learned about the zeta potential and the destabilization of the colloidal particles. And then we moved on to discussing about the coagulation, like what are the different types of coagulants, what is the compression of a double layer, what is absorption and charge neutralization, the sweep coagulation, and how we can do coagulation with the help of alum, and what is the alkalinity requirement. So this was the brief overview of the concepts which we saw in week 7. And now we will be solving some of the questions, both subjective and objective. So we will go through the question one by one. Okay. So this is the first question, which is related to the population forecasting, where it says that forecast the population for the year 2041 based on the population data given below using arithmetic increase method, the geometric increase method, the incremental increase method. So we have been given the populations corresponding to 5 different years, starting from 1961 to 2001. So the populations are given in a for a period of 10, 10 years. So per decade, what is the population it has been given? So you have to forecast the population for the year 2041. And we have to use all the three methods, starting from the arithmetic increase method, the geometric increase method, and the incremental increase method. So I'll give you some time to note down the population, and then we'll see how to find out the how to forecast the population for a given period of time. Please note down the populations corresponding to each year, so starting from 1961 to 2001. Okay, so we'll see how to solve this problem. We'll start with the arithmetic increase method. So I will open my notepad. Okay, I hope that you can see the screen. Okay, so the first question. Uh, so we know we have the year and we have the corresponding population. Fine. So it is first is 1961, 1971, 1981, 1991, and 2011. The corresponding population that is being given are, uh, we can say 6848, 13308, 36747, 58242, and 82149. So these are the populations. So if we find out the change in the population. So first we have to find out the change in the population. So if we see the change in the population, so with respect to 1971, what with respect to 1961, what is the change in 1971? So if we subtract these two, we will get 6460. Similarly, with respect to 1971 to 1981, we will get the changes 23,439. So we have to just subtract the populations. So in this way, we will get the change. So I think these are the four changes we can find. So we have to just subtract these population from the earlier population. And then we will find out the total. So if we add all the changes, we will get 75,301. Okay, and also we have to find out the average. So the average of these population will be equal to 18,825. So we got the total and the average. So now we have to, now the first one is the arithmetic increase method. So at 2041, so if we see the number of decades from 2001 to 2041, it is 4 decades. So 4 decades. So our n will be equal to 4. So the population at 2041 will be. So what is the known population in 2001? It is 82,149. So plus the number of decades, that is n, that is 4, into the average increase in the population, which is 18,825. So if we calculate that, we will get the answer as 157,449. So this will be my population at 2041. So I will quickly go through the method of arithmetic increase method. So what we did, we will find the change by subtracting the two populations back to back. So we will subtract the population of 1971 from 1961. So like that we get the changes. Then we will calculate the total population and then the average population. So we will calculate the number of decades, that is 4, which will be my n, and the population in 2041 will be the last known population plus n into the average population change. So that will be the answer for the arithmetic increase. Now we will we will have to find out the answer for geometric increase method. So for that, what we will do, we will find out the percentage change. We will find out the percentages. So the first percentage change will be, suppose the change was 6460 and the population at 1961 was 6848. So my percentage change will be 0.943. Okay. Similarly, for the next year, it will be 23439 divided by 13304. So my percentage will be 1.765. So like that, I will find out the percentage change. So please calculate the other two percentage change by yourself. Try to do this. I hope you have been able to find out the percentage change. So for the other 2 years, it will be 0.585 and then 0.410. So we will find the percentage change. Now we have to find the geometric mean of these percentage change. So if we find the geometric mean, it will be equal to around 0.795. Okay, so this is my geometric mean. So we will see how to find out the population. So again, my n will be equal to 4. Okay, so my n will be equal to 4. So now the population at 2041 uh, with the help of the geometric increase method will be 8, which is the last known population, then 1 plus R. So my rate will be 0.9795, which we find out this, which is the geometric mean. So this geometric mean. So 1 plus 0.795 to the power the number of decades. So that is my whole. So it looks like a compound interest formula. So where this is the P and this is R and this is N. So like that we can find out. So this is nothing but the compound interest formula. So if we calculate this, we will get the answer as 852,331. So we can see there is a drastic change in the population forecast in the case of arithmetic increase method and in the case of geometric increase method. Okay, because since we are uh, assuming in the geometric increase method that the population will increase exponentially, so that's why the population will be much higher with respect to the arithmetic increase method. So for comparatively newer cities, we will use this geometric increase method. And then we will see how to do for the incremental increase method. Okay. So I think, okay. So we can use the same table. I hope you have written all these things. Just take a screenshot of it or write it down again because I will be using this table again. Okay, so I'll just remove the percentage change part. Okay, so now instead of the percentage change, we'll find out the incremental change. So it is nothing but the change in the change column. So again, we will do what we will do. We will subtract 6460 from 2349439. So what we will get? We will get something around 16,979. Again, we will subtract this from this. So it will be 1944, but this time it will be minus, and again we will subtract like this. So we will get 2412. So this is the incremental changes, change in the change. So if we find out the total, so the total turns out to be something around 17,447. Okay, and the average turns out to be 5816. Okay, it's pretty simple. Just we have to do subtraction for the change column. So okay, so we'll now see how to find out. So again, here n will be equal to 4. So my population at 2041 would be equal to the known population plus n. N is 4 into the average change. So my average change was equal to 18,825. Now again, incremental change. So incremental change will be n into n plus 1 by 2. So it will be 4 into 4 plus 1 by 2 into the average of the incremental change. So that is 5816 into 5816. So it will be equal to, so this n into n plus 4 into 4 plus 1 by 2 will become as 5 into this. So my final answer will be 215607. So we can see that the population in the case of incremental incremental is somewhat in between the geometric and the arithmetic increase level. Okay, see, it is considering this extra term here. So this is nothing but n into n plus 1 by 2. Okay, I hope you understood the problem. So I'll just quickly give a recap of this. So if we know the population of each of the decade, okay, so this is known. So for arithmetic increase method, we will just find the change. We will just find the change. And we subtract one from the two consecutive decades population, and then we will find out the total and then the average. So in the case of arithmetic increase method, it is just the last known population plus the number of decades for which we want to find out the population into the average. Whereas in the case of geometric increment, we will find out percentage change. So percentage change for this term will be 6400 So like that, we will find out the percentage change and we will find out the geometric. And then with the help of the compound interest formula, the last term population and plus this value, which is the R, and this we will calculate the geometric population. And then in the case of the incremental increase method, we will have to actually same till here for the arithmetic increase method plus the incremental change. So I will find the incremental change. We will first calculate the incremental change for all of these tickets. So these are the incremental change. So here we have to take care of the positive and negative sign. Because sometimes the incremental change can be positive, sometimes it can be negative. So we have to take care of that and we have to incorporate them in our total average. So once we get the total average, and this one, the average. Like that, we will be able to calculate the calculation for the conversion forecast. Okay. I hope it's useful to all of you. Now if we move forward, we'll see the problem. Okay. So I've given the solution also here, so you can process. So this is the arithmetic increase method, then the geometric increase method, and at last we got the incremental increase. Okay. So now we'll discuss the second problem. So it says that a water sample is analyzed for coliform organisms by the multiple two fermentation method. So the results are confirmed of the confirmed test are given as follows. So if we have three different sample sizes, 0.01, 0.001, and 0.000. And we have also been given the number of positive and the negative tubes. So positive and negative tube means in how many tubes out of five we are getting bubbles. So if bubble formation is there, then it means a positive tube, and if there is no bubble formation, then it is a negative tube. So the number of positive and negative tubes are given. Now we have to calculate the NPN, that is the most probable number of coliforms per 100. Okay, so to solve this problem, we also need the NPN table. So except of the NPN table is given here. So possible combinations of possible of positive tubes are given, and the NPN index per 100 index is also given. Most of the time we have to solve it with the help of the NPN table. Okay, so this is the overall question. Please picture it once again and then we will discuss how to solve this problem. So if you talk about just multiple team fermentation method, I will just give a brief. Suppose we have three sets of test tubes. So in each set we have five test tubes. So each of the test tube we will provide the sample and we will also provide some nutrient or you can say the food for the microorganisms. Suppose my samples, the microorganisms may or may not be present. So the important probability statistics we tend to find out that how much microorganisms are present. So in the first set of five test tubes, we will put 0 point or you can see how much is given here. Okay. So 0.01 ml of sample is given. Okay. And the next five tubes, they have given 0.001 and the other next five they have given 0.0001 plus some nutrients and nutrients are food for the bacteria. So after incubating for some period of time, we can see there are small Dylan tubes in each of these tubes. These are called Dylan tubes. It is nothing but inverted tubes. So if any microorganisms are present, then there will be definitely some gas formation and it will be collected in this. Okay. So by the positive tube, so we are saying it's positive tubes and negative tubes. So by positive tubes, we meant to say that there is gas formation, which corresponds to that there is some bacteria or some microbes, and in negative tubes, there is no gas. So what the question says that for the set of 0.01, we have it says that we have five positive. So all of them have got yes. For the next set, we have three positive tubes, and the next set we have one positive. One or two. I think it's one. So if we see the combination of positive tubes, we are getting it as 5, 3, 1. So this is the combination of the positive tubes. So 5 corresponding to the first set, then the second set, then the third set. So 5, 3, 1. Now we will see the NPN chart. So if we see the NPN chart, on the left side there will be this combination, and on the right side there will be NPN. So for this 5-3-1 combination, we have to see the corresponding. Okay, so that chart must be available with you. Otherwise, the charts are this problem. So you will see the chart. So in this chart, we can see that corresponding to 5-3-1. Okay, the NPN index is 100. The NPN index is 110 per 100. So one might say that the answer of this question is 110. But that is not the case. We have to take care of one more thing. Now, this NPN index chart is given for the combination of positive results when the test tubes used for dilution is of 10 ml, 1 ml, and 0.1. Okay, so for the sample size of 10, 1, and zero point 0.1, this chart is given. But in our question, the sample size which we have taken is 0.01, 0.001, and 0.000. So there is an order difference of 1000. because instead of 10 ml, we have taken 0.0 as my first sample. So there, if we divide 10 by 0.01, we will get 1000. So there is an order difference of 1000. So what we have to do, we have to simply multiply this order difference with our NPTEL. So for 531 combination, the NPTEL index is 110. Now there is an order difference of 1000. So we multiply 110 with 1000. So we will see the solution. So at first, we have to find the composition of positive tools of our sample. So here it is 531. Now find the NPN index from the NPN table. So for 531, the NPN index parameter is 110. Now what the sample size is for 0.01, 0.001, and 0.201. But the table is given for 10, 1, 0.1. So the order difference is 10 by 0.01, which is 1000. So we'll simply multiply the NPN index. I hope it's understandable to all of you. So the final answer is that 10,000 or 100. This is the answer. Okay. Shall we move to the next problem? I hope it is clear. Move to the next problem now. So next problem again related to the multiple fermentation test. So it says that a standard multiple fermentation test is run on a sample of water from a surface stream. The results of the analysis from the tests are given below. Determine the NPN using the Thomas equation. Okay, so here we have to use the Thomas equation. So again, the sample size is given. We have been given the number of positive results and the number of negative. But we have to find out the NPN with respect to the Thomas equation. We will see what is the Thomas equation and how we have to find out. So just make a note of these questions so that we can move forward and solve this. Okay. So now the third question. So if you see the Thomas equation, it's something like this. NPN per unit ml by number of positive tubes divided by square root of ml of sample in negative tubes. So this is the number and ml of sample again under in all tubes. Right? So this is the equation for the Thomas equation. So what is the number of positive tubes? So the number of positive is 4 plus 2 plus 1 is 7. Okay. Now ml of sample in negative tubes will be 1, okay, 1 into 10 plus 3 into 1 plus 4 into 0.1 plus 5 into 0. So this 10, 1, 0.0.01 are my sample. So since in the first set 4 were positive, so 1 will be negative. Then 2 were positive, 3 will be negative. 1 was positive, 4 will be negative. When 0 was positive, 5 will be negative. Like that we have spent. So the total will be around 13.07. And then we will find out the ml of all samples. Okay. So it will be
We have total of 5 in 5 into 10. Okay. And 5 into what? 5 into 5 into 5 into 5. So we simply substitute. So and given 500 7, right? 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 Given 5, 5, that is the previous, we get answer as 26. Yeah, we can just say 26. So the answer for this question is 26. Okay, we have understood the problem. So simply we have to just constitute the non-positive diff, then the sample negative diff, and then the sample. Right? So this is the solution. Now we move to the okay, so again, so we give it from the minus 6. Okay, I will give it. The next problem. Now calculate the fire demand of the population of 1656 using the Dixon's formula. The fire demand should be given. Use the Dixon's formula. Calculate the fire demand. So here we have to take care. We have to take care about the units. So on this formula, we have the answer in some different units. Here the demand is as per liter per second. Just to show that the units are proper. So if you see the question formula for fire demand, okay, so for fire demand, yeah, what the question is C1 is to but here the fire demand is dividing liter per minute. Okay, since it's a direct formula, so we have to take care of the units. And P should P is the population, but with thousands. Well, then we have to take care of this. Hence, it's a differential equation. So we have to take care of it. So my FD what? P is given as 1656, but that is 1656 total. So in thousand, it will be 1656. Right? So the answer will come out as 14. By the same formula, you in liter per minute is given as 318. The next problem. Okay, so we have a matched up solving type. So we have given four categories: chemical, physical, biochemical, and microbiological. Which category corresponds to what factors? So the options are given. Let's try to go through. I think the answer is C. So, for chemical category, we have the salinity, hardness, and alertness. These are chemical properties. And then for physical, we have the taste and odor and temperature. For biochemical, we have the DOD and the DOC. So, we use the biochemical oxygen demand. And then for the microbiological parameters, we have the pathogens, the volatile suspended solids, and the ion. Mostly the volatile suspended solids are a measure of my biomass. So that's how we use there. This time, we just match the correct category. So it says that this zeta potential is the electric potential, the shear plane of the particle surface. It's true. So the collaboration theory will learn about the vector potential, which has to be overcome. So that it can it says that the vector potential is the electric potential between the shear plane. Just think about it. It's true. So the correct answer is false because the vector potential is the electrical potential between the shear plane and the bulk solution. It is not the particle surface, it is the bulk solution. Okay. Particle solution. Potential difference between the shear plane and the particle solution is clear. It says select the correct characteristics of a molecule. Answer combination. We have some characteristics. The correct thing for the molecule. Whether it should be non-toxic at working dosage, should be having high charge density, should be having a low charge density, insoluble in neutral pH range, soluble in neutral pH range. These are the characteristics given to find out the correct one from the question. Okay. Okay, so we will see the statements one by one. So it says non-toxic at working dosage. So a coagulant must be non-toxic. Otherwise, there is no point of using that coagulant. And then talking about the charge density is very high for a coagulant. So option B is also correct that it should be having very high charge density. And if we see the performance at neutral pH range, then it should be insoluble. Okay, but because if it's soluble, then again there is no uh, use of a coagulant. So the correct options are A, B, and D. Okay, so it should be non-toxic at working dosage. It should be having a high charge density, and it should be insoluble in the neutral pH range. So this was the seventh question. Now we move to the next problem. Now it says that about coagulation theory, the net force on the colloids is repulsive at greater distances and becomes attractive only after passing through maximum net repulsive force called the energy barrier. The above statement is relevant to which of the following mechanisms? Is it ionic layer suppression, interparticle bridging, sweep coagulation? None of the above. So again, going through the statement, it says that the net force on the colloids is repulsive at greater distances and becomes attractive only after passing through maximum net repulsive force called the energy barrier. So this is relevant to which of the mechanism? So we have learned about four absorption mechanism. Three are mentioned here. Other one is the absorption and charge neutralization. So for which of the following it is true? So if we see in the case of only ionic layer compression, okay, it has to overcome the distances and so that the attraction forces are more so that the particles can come together and then settle down. Okay. So in the case of only ionic layers compression, this theory holds true and it is relevant. Not holds true, it's relevant. So the correct option is option A, that is the ionic layer compression. Okay. Whereas the interparticle bridging, it is just the in the long change in the long change polymers, how the particles are getting attached. And same case in the case of sheath coagulation, how the gelatinous flaws are formed, like in the case of alum or Al3 plus. So the mechanisms are different, whereas there is a repulsive and attractive force concept in the case of the ionic layer compression. Okay, so option A is correct. Okay. Now again, a small numerical, it says that the following information about a community is given below. The present population is 34,000 and the expected population is 20 in 20 years is around 52,000. And the present water consumption is around 3,700 meter cube per day. And the treatment and the plant capacity for which it is designed is 600. So we have to assume arithmetic rate of population growth and find out the number of years from now when the plant will reach its design capacity. Okay, so the present and the expected or the projected is given. So we have to find how many years, uh, in how many years the community will reach the design capacity. It's a simple problem, just try to understand it. Go through the problem once again and we will discuss it. Okay, so we'll see the solution. So this is question number 9. So the present population is around 34,000. The expected population is around 52,000. So if you find out the average increase of population per year, so it will be 52,000 minus 24,000 divided by 20, because this expected population is given in 20 years, right? Divided by 20, so my per year population increase is around 900. Okay, this is the average. Now the present water consumption, if you see, it is designed for 3700 meter cube per day, and the design capacity is 5600 meter cube per day. So to reach max capacity, so it will be around 5600 minus 3700. So that is around 1900 meter cube per day. So more 1900 meter cube day of more uh, water consumption can increase. Okay, so this is the difference. So now if we calculate the present average water consumption per head per day. So per capita or per day, how much water is being consumed if we see. So the total water consumption is 3700 divided by the population of the present, that is 34,000. So it will be around 0.1088. So this much amount of water per head per day is required. Okay. So meter cube per capita per day. So now we know that per year 900 people are increasing. So increase in consumption of water each year. So in each year, how much consumption is increasing? So we will simply multiply 900 into 0.1088. So it will be around 97.9411 meter cube per day. So this much amount of meter cube per day is increasing per year. So in how many years it will reach the design capacity? So number of years to reach the design capacity will be the difference between the design capacity and the present thing, that is 1900 divided by 97.941. So it will turn out to be 19.4 years. So in 19.4 years, it will reach the design capacity. Okay. So this is the overall problem. Basically nothing. Just you have to find out like how much will be the increase per year of population, how much of the water consumption difference is still present, what is the per capita use now, and per year how much increase will be there, and then the number of years to find to reach the design capacity. So it will, if it is around 19.4 or around 20 years. So this was the overall problem. Okay. I hope it is clear to all of you. If you want, you just can go through it once again. Right? Okay. So this is the answer. And I also added it here. You can check the PPT later. Okay, so the next question now. Compute the fire demand for a city of 1.5 lakh population by using the formula of America Insurance Association, or also known as the National Board of Fire Underwriters formula commonly. So we have to find out the fire demand. And the answer should be in MID. Just try to recall the formula for the National Board of Fire Underwriters, or it are also known as America Insurance Association. You will see the formula for this. So the formula is given as Q in liters per minute is given as 4637 under root P into 1 minus 0.01 under root P. So again the discharge here empirically is found out to be in liters per minute, and the P is the population in thousands. So again the same funda in thousands you have to find out. So it is given for 1.5 lakhs. So in thousand it will be 150. So 4637 root 150, 1 minus 0.01 root 150. Okay. So it will turn out to be 4985.9 liter per minute. And in MLD it will be 71.73763. So we have to report the answer in MLD. So it will be 71.763 MLD. Okay, but the actual answer will come in liters per minute. So just we have to take care of that. Okay. So I hope it's clear. It's a very easy and direct question. So this is the answer. 71.76, around 72 MLD will come. Just make sure that you are putting P in thousands, that is the population in thousands, and the final answer is in liter per minute. Okay. Okay, so next problem. If the average daily demand of a city is 150,000 meter cube, the maximum daily consumption will be. So here we have to make use of the peak factors or the other daily, hourly, or weekly factors. So the average daily demand is given. So we have to find out the maximum daily demand. Okay, so what is the factor? That is the question. What is the factor that we have to multiply with? Okay, so the correct answer is 270,000, because the factor that we use as for the daily variation factor is 1.8. So from average daily demand to maximum daily demand, if we have to find out, we have to multiply it with the factor of 1.8. So 150,000 into 1.8 is 270,000 meter cube. So this is the answer. Okay, we'll move to the next problem. Match the typical water quality parameters with the respective categories. So again, we have a treatment unit and the respective function. So we have aeration, softening, coagulation, and filtration. So what different functions do they perform? We have to match with it. So please try to find out. Go through the question once again, and then we will discuss. Okay, so if we see here, the aeration unit will be used to remove the color, odor, or taste. The softening unit is obviously for the hardness, where we have to remove them. And then the coagulation unit can be used for the suspended matters. And then the filtration unit can be used for the colloidal dissolved matter or the bacteria. So if we match all this, we'll get the answer as C. So 1B, 2D, 3A, and 4C. Okay, it's very simple. I think you can make out easily. Okay, the next question. Select the correct statement regarding the coagulation. So it says that alum coagulation produces aluminum hydroxide flux in flocculation process. Alum coagulation decreases pH in water. The zeta potential of a particle is increased during coagulation, and the correct sequence of treatment of a typical turbid surface water is coagulation, flocculation, sedimentation, and filtration. So four statements are given. We have to find out the correct answer. I think here, as far as the answer is concerned, only one of the statement is incorrect. So if you see all the statements one by one, so alum coagulation produces aluminum hydroxide flux. So that is true. And also alum coagulation decreases the pH because we know alkalinity is directly related to the alum coagulation. It takes up alkalinity. So it will decrease the pH. So option B is also correct. Now the zeta potential of a particle is increased during coagulation, which is not true because the zeta potential will be decreased in the case of coagulation. So option C is incorrect. And the other thing, the correct sequence, it is also fine because after coagulation we go for flocculation and then sedimentation and filtration respectively. So option A, B, and D all are correct. Okay, so this was about the 13th question. So except for the C statement, because the zeta potential will be decreased during the coagulation process. So option C is incorrect. Move to the next problem. Match the following points marked on the graph with the concentration given below with respect to the effect of concentration on electrical double layer. Okay, so it's talking about the electrical double layer. So we have three different concentrations of NaCl: 600 milligram per liter, 60 milligram per liter, and 66,000 milligram per liter. So we have to find out the correct option, which is depicting the effect of concentration on the electrical double layer. So we have to just have to see the distance of the electrical double layer. So if you see, the curve will move closer to the y-axis, or the distance will reduce if more and more particles or concentration is there. Okay, so in that case, the farthest away will be the least concentrated particle, the solution. So we can say that 60 milligram per liter of NaCl, that is the second option, will be the A curve because this is the farthest away. Okay, so the correct answer is C, that is 2A, 1B, and 3C. So 60 milligram per liter will be the farthest away. And in between, we will have the 600 milligram per liter. And then the closest to the y-axis, that is the least distance, is for the third, or with the maximum concentration, that is the 6,000 milligram per liter. Okay, so this is the correct option for C. We'll move to the next problem now. In a water treatment plant, the optimum time of flocculation is usually given as 30 minutes. In case the time is increased beyond this value, the flocks will A. Become heavy and settle down in flocculation itself, break up and defeat the purpose of flocculation, stick to paddles, and there will be no change. So what will be true in the case if we increase the optimum time of flocculation more than 30 minutes? Just think over it, go through the question again. So will they become heavy and settle down in flocculation itself? Will they break up and defeat the purpose of flocculation? Will they stick to paddles or there will be no change? So obviously the answer will be B. They will break up and defeat the purpose of the flocculation because more time it's given. There can be a change, case of charge reversal also. Okay, so that can also cause breaking up. So mostly if more and more time is given, there can be breaking up of the particles, and it will defeat the whole purpose of the flocculation. So option B is correct in this case. Okay. Again, a small numerical. A certain water needs 12 ppm alum dosing. The amount of alum needed for 10 mld of water in quintals per day. Or rather, since the options are given in kgs, so let it be. So the amount of alum needed for 10 mld of water in kgs per day. So rather than quintals, let it be in kgs per day. To find out the answer, the concentration is given as 12 ppm of alum, and the discharge is 10 mld. So we have to find out the total alum requirement. We will see the answer. So it will be 120 kgs. So how we get? So we have the alum dose as 12 ppm. So it is equal to 12 milligram per liter. Okay. The ppm means milligram per liter. So now if we multiply it with the discharge, so 12 milligram per liter into 10 mld. So 10 mld we can write it as 10 into 10 to the power 6 liters per day. And then to convert milligram into kgs, we have multiplied with 10 to the power minus 6. So ultimately it will become 12 into 10. So it is 120 kgs. Okay, it was
Pretty simple direct calculation. We'll move to the next problem. Okay, select the correct statements regarding turbidity. A. Turbidity increase the disinfection efficiency of UV method of disinfection. Maximum permissible limit of turbidity is 15 NTU. Clay, silt, and finely divided particles causes turbidity. Turbidity is a measure of ability to scatter light. Okay, so just go through the statements one again, and we'll discuss the correct answer. If we see the answer that the turbidity increase the disinfection efficiency, so this statement is false because due to turbidity, the disinfection efficiency will be decreased. Okay. Then the maximum permissible limit for turbidity is 50 NTU. Again, it is false. It is 1 NTU or maximum relaxation up to 5 NTU in case of there is no alternate sources. Option C, K silt and finely divided particle causes turbidity. This is true because all these particles will scatter the light, and turbidity is the measured probability to scatter light. So again, option D is correct. So option both C and D are correct in this question. So here it is. The correct answer is option C and D. Now we'll move to the next problem. The quality parameters of rainwater from different sources are given below. So we have source A, B, C, and D, where the quality parameters as per pH, turbidity, TDS, chlorides, and fluorides are given. So water drawn from each of the above sources can be acceptable for drinking without any treatment. So we don't want to do any treatment. So we have to check which of the source is correct, is acceptable for drinking without any treatment. So just have to know the drinking water standards for each of these water quality parameters that are the pH, turbidity, the TDS, and chlorides and fluoride. So, so if you see, so we have the water quality parameters, we have the acceptable limits, and we have the relaxed limit also, based on if any alternate sources are available or not. So we will check. So my first water quality parameter is pH. So the acceptable limit is 6.5 to 8.5. So this is all with respect to IS 10500. Okay. So pH should be, and there is no relaxed limit. Whereas in the case of turbidity, we have 1 NTU and relaxed limit is 5 NTU. Okay. In the case of TDS, it is 500 milligram per liter and 2000 milligram per liter. In the case of chloride, it is 250 milligram per liter and 1000 milligram per liter. Whereas in the case of fluorides, it is 1 milligram per liter and 1.5 milligram. So we have to see each of the sources and whether they are falling in between these acceptable limits. So whichever source is falling, that will be the correct answer. Okay. So if we see option A seems to be the right answer because it is following all the acceptable limits of the water quality parameters. So option A is correct. Fine. We'll move to the next question. A 40 ml of water is being treated with 18 milligram per liter of alum in a water treatment plant. Calculate the yearly alum requirement. If the water contains 5 milligram per liter as CaCO3 of alkalinity, calculate the amount of CaO purity of 85% required. So in a particular water treatment plant, 18 milligram per liter of alum is required for the treatment with a discharge of 40 ml. So we have to calculate the alum requirement in an yearly basis. And also we know that this alum will take up some alkalinity. So now the water contains 5 milligram of per liter of alkalinity as CaCO3. So how much more CaO has to be provided if the purity is 85%? So this is the problem. Make a note of it and try to solve, then we'll discuss it further. Okay, so we'll see how to solve this problem. So we have this reactor where we are adding 18 milligram per liter of alum, and the Q that is coming in is 40 mld. And inside this, we have already 5 milligram per liter of alkalinity as CaCO3. So mostly alkalinity is given in terms of CaCO3. So that is what is given. So the first part, the yearly alum requirement. So quantity of alum required, it is 18 milligram per liter into 40 into 10 to the power 6 liters per day into 365 days, and will convert into in terms of tons, ton per milligram. Okay, so we'll get it as 262.8 tons per year. Okay, so this is the yearly alum requirement. Now we have to find out how much CaO is required. Okay, so this is a thumb rule, and we know that 1 gram of alum reacts with 0.45 grams alkalinity as CaCO3. So by the chemical formula and reaction, we know that 1 gram of alum will react with 0.45 grams of alkalinity as CaCO3. So now here we have 18 milligram per liter of alum, and this will react with 18 into 0.45, which is equal to 8.1 milligram per liter alkalinity as CaCO3. Okay, so the additional alkalinity required will be 8.1, and 5 is already there in the system, so 8.1 minus 5, so 3.1 milligram per liter. Okay, so 3.1 milligram per liter as CaCO3 is as CaCO3 is required. Okay, so now we are doing with respect to the calcium oxide CaO. So we know that CaO will react with water to give the alkalinity as CaOH twice. Okay, so we will correspond this to 1 CaCO3. So this is 1 mole will give 1 mole of this, will give 1 mole of this. Okay, so we can say that 1 mole CaCO3 is induced by 1 mole of 100% pure CaO. Okay, so 1 mole of CaCO3 is induced by 1 mole of 100% pure CaO. Or we can also write 1 mole of CaCO3 is corresponding to 100 grams. 100 grams CaCO3 is induced by 1 mole of CO is 56 grams. 56 gram of CO. Okay. So we need 3.1 milligram per liter as CaCO3. So 3.1 milligram per liter as CaCO3 is induced by how much? It will be equal to 56 by 100 into 3.1 milligram per liter. Okay. Just in statements, we can find out the answer. So the quantity of 85% pure CO, that will be equal to how much? 56 by 100 into 3.1 milligram per liter. Now it is 85% pure, so 1 by 0.85. Okay, into the discharge 40 into 10 to the power 6 and into 365 days. And to convert into tons, we will get 10 to the power minus 5. So this is the overall quantity. So we'll get it as 29.8 tons per day. Okay, so I think it's pretty simple. So 29.8 tons per year of CA is required to do the coagulation. So we can go through it once again. So first we will calculate the alum requirement. Directly we will multiply it with the discharge. Then we know that 1 gram of alum reacts with 0.45 grams of alkalinity as CaCO3. So 18 milligram per liter will react with 8.1. So now 5 is already present in the system. So 8.1 minus 5, additionally 3.1 is required. So now 1 mole of CaCO3 is induced by 1 mole of pure CaO, or we can write it as 100 grams of CaCO3 is induced by 56 grams of CaCO because of their molecular weight. So 3.1 will be induced by 56 by 100 into 3.1. So for 85% pure, you have to just divide by 0.85 into the discharge into the number of days, 365 into the unit conversion, whatever is required. So we get it as 29.8 tons per year. Okay. So this was all about the question. So the correct answer is 262.8 tons per year and 29.8 tons per year. Okay. Okay. So thank you everyone. So these many questions I had for this week 7. So the next session will be again on 15th of March 2024, again on Friday from 7 to 9 p.m. So this is my contact detail. So you can ping me if you have any other queries or anything you wanted to ask or any study material if you want to access. So you can always contact me in this email ID, that is saha19akash@gmail.com. Okay. So thank you everyone.